Welcome to this special briefing from the Tensor Security Academy. We're about to dive into something pretty fundamental, how we build trust in a world made of ones and zeros.
I'm Tensor, and I'll be your guide. What we're doing today is decrypting the essential ideas of modern cryptography, and we're using the foundational first chapter of the Handbook of Applied Cryptography as our map. My goal here? To give you a solid framework for how all this digital trust stuff actually works.
So this is the fundamental problem, right? In a digital world, everything is just data, and data can be copied perfectly, infinitely, at zero cost. It's a question visionaries like Ron Rivas posed. If you can copy a digital dollar as easily as you can repeat a rumor, how do you create value? How do you create trust? All right, here's our mission briefing for today. First, we'll break down that digital trust problem. Then, we'll look at the toolkit we've built to solve it. After that, we'll get into the public key revolution, a real game changer. We'll see how these tools become systems, and finally, we'll talk about the constant battle that's always being fought.
Okay, let's dive right in. Before we can build anything, we need to know what we're trying to achieve. What are the core security objectives we absolutely have to nail down in any digital communication?
So these four goals, they're really the bedrock of all information security. You've got confidentiality, which is just about keeping things secret, think private messages. Then there's data integrity, making sure the information you receive is exactly what was sent, no tampering allowed. Authentication is all about proving you are who you say you are. And finally, non-repudiation, which is a fancy way of saying you can't later deny you did something, like signing a contract. Achieving these requires a very special set of tools. Okay, so we know the problems we need to solve. How do we actually do it? Well, we have a foundational toolkit, a set of what we call cryptographic primitives. Think of these as the fundamental building blocks for creating trust. So, to solve that confidentiality problem, our go-to tool is symmetric key encryption. The concept is super simple. Two people share one single secret key. It's kind of like having a physical lockbox where you both have the exact same key. It's fast, it's efficient, but it has this one giant glaring problem. How in the world do you get that secret key to the other person securely to begin with? All right, what about proving who you are and making sure you can't back out of a deal? For that, we have digital signatures. This isn't like scribbling your name with a stylus. Nope. This is a powerful, unforgeable, mathematical seal that binds your identity to a piece of information. There's no faking it. And for our last tool, to handle data integrity, we have hash functions. These are amazing. You can feed a hash function anything, a single word, the entire Library of Congress, and it spits out a unique, fixed-size digital fingerprint. It's a one-way street. And here's the magic. If you change even a single comma in the original data, that fingerprint changes completely, so any alteration becomes instantly obvious. Okay, let's circle back to that huge problem with symmetric keys, right? How do you share the secret in the first place? Well, the solution to this was so profound, it wasn't just an improvement, it was a revolution. It completely changed the game. This really lays out the two different ways of thinking about it. With symmetric key, it's like a shared safe combination. Both you and I need to know the same secret code. But with public key, now that's different. It's more like a personal mailbox. Anyone can drop a letter in the mail slot, that's the public part, but only I have the private key to open the box and read my mail. And how does this mailbox trick work? It's based on this brilliant mathematical idea called a trapdoor one-way function. It's a calculation that's super easy to do one way, but practically impossible to reverse. Unless, that is, you have a secret piece of information, a trapdoor. Your private key is that trapdoor. And just like that, you can have a secure conversation with someone you've never met without needing to share a secret key beforehand. Absolutely revolutionary. Now here's a really crucial point. These tools we've been talking about, encryption, signatures, hashes, they're like individual ingredients in a kitchen. You almost never use just one by itself. To actually build the secure systems we use every day, you have to combine them into complex recipes. And these recipes, we call them cryptographic protocols. A protocol is just a distributed algorithm, a set of steps that different parties follow. They combine primitives like encryption and signatures to build something bigger, like, say, the secure connection that gives you that little padlock icon in your web browser. That's a protocol in action. But, and this is a huge but, all of these amazing tools and protocols have to operate under one critical assumption. There is always someone out there, an adversary, who is actively trying to break everything you've built. It's a constant battle.
Let me show you what I mean with the classic man-in-the-middle attack. Look at this. Alice wants to talk to Bob, so she asks for his public key. But an attacker, Eve, intercepts that request and sends her own public key back to Alice. Now, Alice, thinking she's talking to Bob, encrypts her message with Eve's key. Eve can now decrypt it, read it, re-encrypt it with Bob's actual public key, and send it along. Alice and Bob think they're secure, but Eve is reading everything. This shows you why just having a public key isn't enough. You have to be absolutely sure it's the right one.
So when cryptographers design these systems, they're always thinking about what the attacker can do. The weakest attacker can only listen in. That's a ciphertext-only attack. But what if the attacker is more powerful? A known plaintext attack means they've somehow gotten their hands on both the original message and the encrypted version. And the strongest? A chosen plaintext attack. This is where the adversary can literally trick your system into encrypting anything they want to see how it responds. A robust system has to stand up to even that. And that brings us to this quote from Ron Rivest again, which just perfectly sums up the entire field. Cryptography is about communication in the presence of adversaries. It's not just about math, it's about a fascinating, game-like battle. It's a constant chess match between the people building the systems and the people trying to tear them down. So, what's the big takeaway here? It's this. The trust we all rely on every single day, for everything from digital cash to secret documents, it's not built on hopes or handshakes. It's built on a mathematical blueprint. Cryptography is what creates certainty and trust in a world where data is otherwise so easy to copy and change. So, today we've really covered the what and the why, but there's still the how. To continue your training, make sure you join us for our next briefing, where we'll dive into Chapter 2, the mathematical background that makes all of this magic happen.